A very good morning to one and all present here. Uh, Once again, I thank the AICTE for giving this opportunity of having expert lecture for the benefit of faculty members and students across India in the title uh, Distinguished Chair Professor Scheme. And I am delighted again, and I am really most delighted for welcoming Professor Prem Vrat. I have already given a brief and a detailed profile of Professor Prem Vrat, who has been again called for the second expert lecture in the title Industrial Engineering 4.0, a new paradigm. Professor Prem Vrat has a lot of credentials which probably each and every faculty member and students should know. And this type of scheme, distinguished professor scheme, is a scheme wherein the faculty members and the students can understand and can get the lot of knowledge from experienced professors like Prem Rath. Just to regain again for the newcomers who across India, all over from India, from many engineering colleges who will be coming to this virtual meet. I would like to again tell about Professor. He is now the chairman of Board of Governors of Indian Institute of Technology, Dhanbad, with additional charge as chairman Board of Governors of IIT Mandi, an outstanding academic. Professor Vrat is the Pro-Chancellor, Professor of Eminence and Chief Mentor at the North Cap University, Gurugram. Just prior to joining ITMU as the Vice Chancellor in September 2011, he was Professor of Eminence at the Management Development Institute, Gurugram. Professor Vrat was Founder Director, IIT Roorkee, Vice Chancellor, UP Technical University, Lucknow. Now it is known as APJ Abdul Kalam Technical University, Lucknow. Professor, Head of Center for Management Studies, Coordinator, Applied Systems Research Program, Dean, Deputy Director and Director Officiating at IIT Delhi, Professor and Division Chairman of Asian Institute of Technology, Bangkok. He is an honorary professor at IIT Delhi and distinguished adjunct professor at AIT Bangkok. He is AICTE Distinguished Chair Professor now. He was Chairman, Board of Governors of WIT, Dehradun, a constituent institute of Uttarakhand Technical University. He was an honorary research fellow at the Department of Engineering, Production, University of Birmingham, United Kingdom, and as an international visiting fellow at University of Western Sydney, Australia. He has extensive experience of more than 52 years in teaching, research, management development, and consultancy. Once again, we are very, very happy to welcome our distinguished chair professor, Professor Prem Vrat, for this second lecture of series. And I welcome all the participants across India in all the engineering colleges, the faculty members and the students for hearing this second lecture, Industrial Engineering, a New Paradigm. Over to Professor Prem Vrat. Thank you everyone for joining in this virtual meet. Thank you.
Thank you, thank you, Professor Natarajan, and good morning to all the uh, persons logged in for attending this virtual meet. I am happy to be associated once again in the scheme of AICT Distinguished Chair Professor, linking me with the AICT affiliated institutions, and the topics that I'm speaking on uh, are the topics that are given to me. And therefore, I believe that industrial engineering must have been of some relevance to the Hindustan Institute of Technology, which has given this topic to me. And I, for one, believe that industrial engineering is going to be uh, ever relevant uh, in making competitive advantage, and therefore, at one point in time, this was one of the most sought after discipline. As I myself, after graduating from mechanical engineering in IIT Kharagpur in 1966, I had my master's degree in operation industrial engineering and operation research in 1968 from IIT Kharagpur, and that time that was the only IIT in the country giving a degree, master's degree in industrial engineering, and the competition for that was so enormous that only the people with the highest of the academic credentials could get in. This trend remained for some time. And as you know, that one of the National Institute of Industrial Engineering, NITI, Bombay, was set up in 1963 through ILO. And NITI itself had a very powerful role. It still continues to be uh, an important centrally funded institute, National Institute of Industrial Engineering. Earlier it was called National Institute of Training in Industrial Engineering. So the nickname NITI remains, although it's called National Institute of Industrial Engineering. Now, the reason why I have, in fact, I must also mention that this was a keynote address I had delivered at NITI, Mumbai, a few years back on on the day of their inauguration of an international conference, and the topic is uh, uh, relevant to me because that's the profession that I lived all through my life, and I feel concerned about the decline in the importance industrial engineering is receiving in the country and the institutions, and the preference of the students in opting for industrial engineering as a career option. And based on that, I thought of raising these issues and concerns, and found a newfound opportunity for industrial engineering uh, as a profession in the emerging paradigm of Industry 4.0. As you know that uh, Industry 4.0 or 4.0 is one of the most talked about emerging technological paradigm in the internationally. And India has been a very major enthusiastic partner in debating about Industry 4.0. So much so that there are enormous number of conferences, international conferences and studies talking about India. Niti Aayog has been, in fact, championing the cause of Industry 4.0. Given that context of emerging paradigm of Industry 4.0, and to revive uh, the concept of industrial engineering, which in my opinion, unfortunately, it is uh, not getting that degree of uh, attention as it ought to. And I, for one, believe that industrial engineering would never ever become outdated. Because if you look at industrial engineering as a profession, it deals with enhancing productivity, it deals with reducing costs, it deals with enhancing quality, it deals with eliminating waste, delighting customers. So, at no point in time, irrespective of the changes taking place in the society, industrial engineering would never be out of fashion. It's not a fashionable concept. But since in the recent times, the kind of preferences to industrial engineering as it ought to be is dwindling down, and this actually was the reason why I have given this lecture, which indeed was very extensively appreciated by NITI people, and they said that they'll be giving this uh, lecture. They recorded it to almost every batch that enters NITI, so as to understand that this is an area, this is a subject, and to me, industrial engineering should be almost an integral part of every engineer and manager, because irrespective of domain knowledge, suppose you are a chemical engineer, a computer engineer, or chemical or mechanical engineer, or electrical engineer, whatever you do, you ought to do it with high productivity, low cost, customer orientation, reduce costs, eliminating waste, and therefore, irrespective of the domain in which you're working, industrial engineering becomes relevant, and that's why in IIT Delhi, in IIT Kharagpur, where I studied, and when I joined IIT Delhi in 1968 as a lecturer, we started our program of Masters in Industrial Engineering. It's still continuing, and I still teach there as an honorary professor. To me, uh, industrial engineering is most relevant to India, particularly if you're talking of making India Atmanirbhar and making our local products globally competitive. Making products globally competitive would mean that we're able to offer value for money. And value for money is quality by cost. So if I'm able to deliver better quality at a lower cost, then I gain that value for money and the competitive advantage so that our products, local products become globally competitive. And there is no other way of doing that other than uh, making full use of the concepts and techniques of industrial engineering. And therefore, with that background, I have developed this lecture to make it still more relevant. Now, why examine why industrial engineering lost its shine when indeed, as I mentioned, that even in for admitting 10 students in MTech in industrial engineering in IIT Delhi, we used to get about 1,000 applications, and for at least 2 days we were busy choosing only those 10 people out of 1,000 applicants for interested in doing industrial engineering MTech IIT Delhi. But this is perhaps no longer the case because many other institutions have started. So therefore, based on that, I thought of reviving this concept because to me, the only way you can make India globally competitive is to integrate industrial engineering concept in whichever engineering and management practices that you have, because uh, this will never be outdated and be almost make whichever sector of the activity you are involving in yourself to, it will make that sector more competitive because after all, as a customer is looking for value for money. That means he is looking for a quality that he needs at a lower cost. And if you are able to delight your customer, so that the single point objective of any organization, irrespective of the kind of business they are involving in, is to delight your customers better than your competitors do. And in delighting your customers better than your competitors do, industrial engineering would play a tremendous role. Now, with this background, I'll open up my PowerPoints, and almost like industrial and industry 1.0, 2.0, 3.0, 4.0, I've developed a parallel analogy of industrial engineering 1.0, 2.0, 3.0, 4.0. And therefore, the current industrial engineering 4.0 paradigm is primarily inspired by the concept of industry 4.0. And here I believe that the kind of uh, 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 the reduction in the uh, attractiveness of engineering profession will be brought back because somewhere with the advent of the management graduates MBA, the somewhere because of that, perhaps uh, the MBA took over the industrial engineering. But then there is no conflict of interest. There is a space for both of them. But industrial engineering has a very specific focus, and therefore to bring that back under Industry 4.0, perhaps with a technological background. After all, industrial engineering does require some engineering background or technological background. The industrial engineers are better suited in dealing with the problems of the emerging technological paradigm in cyber physical systems, and therefore perhaps that's the way we can get again our lost identity. Now I'll share my uh, let me see the entire screen, and I'll in fact share that. Okay, I'll share my screen and industrial engineering. Are you able to see? You have to give me a. Are you able to see this?
Yes, Professor. Yes, yes.
You're able to see. Great, great. Thank you. Okay, that's now. Therefore, my topic is industrial engineering 4.0. a new paradigm. I mean, I call it a new paradigm because uh, I've developed this analogy along with the Industry 4.0 concept, and that means there are four like industrial engineering and Industry 4.0. There are four uh, editions of industrial engineering. I start with I call it industrial engineering 1.0. This is how it started, and I'm sure that many of you, and perhaps that's the way it's being taught even now in most colleges, irrespective of where in fact, it's being called. There are a lot of misunderstanding about the even the terminology industrial engineering, because people believe that anybody working in industry is an industrial engineer. Well, of course, in concept one should be, because if anybody, as I mentioned, industrial engineering can be a mindset. And if you take industrial engineering as a mindset, irrespective of what kind of engineer you are, you would be that. But then the conventional definition of industrial engineering, as given by the American Institution of Industrial Engineers, and has been also adopted by the Indian Institution of Industrial Engineering. As you know, that there's a professional society called Indian Institution of Industrial Engineering, IIIE, which has its headquarters in Mumbai and has branches and chapters all over the country, and perhaps the largest number of membership across the country in engineering profession or in industrial engineering with a very wide background. Now, this definition of industrial engineering, which is actually given in 1957 by IIIE, adopted from the American Institute of Industrial Engineering, to me, if we correctly understand this, in fact, it almost sums up the spirit of understanding the rights perspective. Perhaps it needs to be understood. It needs to be understood. For example, I'm just quoting the definition of industrial learning for those uh, who may not have been exposed to it. And I find many people who are practicing industrial engineering are not exposed to this definition. Industrial engineering is concerned with, now look at each word carries a meaning here, is concerned with design, installation, and improvement of integrated systems of men, metals, and equipment. So, what actually this sentence brings out, that industrial engineering is applicable at the design stage. It could be product design, process design, system design. There are industrial engineering techniques, particularly value engineering as one of the very powerful techniques. It's extremely important at the design stage. You design a process, you design a system, you design a product. And therefore, industrial engineering can be applicable at the design stage. It is equally applicable to the installation stage. For example, when you're setting up a company, you are implementing a project, uh, you're overhauling an equipment, as you take it as a project, scheduled maintenance, and therefore industrial engineering concepts are applicable at the project stage, installation, improvement. Installation is many of the project management techniques or network-based planning and control techniques of project management are primarily industrial engineering techniques, and therefore you can apply industrial engineering at the installations, uh, setting up companies or implementing projects. And improvement is application of industrial engineering and in an ongoing company in a dynamic sense. That means, now what does it mean? The potential application of industrial engineering is valid uh, at the concept stage, when you're developing a concept of a product or a process, in implementation, installation, and in the improvement of an existing enterprise. Can somebody unmute, because I see a lot of noise in it. I see a lot of noise. Yeah, kindly unmute yourself so that there's no. Uh, therefore, what the first sentence brings, that the industrial engineering techniques are applicable across the entire spectrum, the design stage, at the installation stage, and in the improvement of ongoing systems. So that means even in existing enterprises, every company. And the great thing is, in manufacturing as well as services. So the techniques of industrial engineering are as much applicable to service systems as in manufacturing systems. For example, you can apply industrial engineering techniques in hospitals, in hotels, in warehousing, in transportation, and whatnot. as much as in manufacturing. So it's a wrong notion that it can only be applied to manufacturing. Therefore, uh, then another important point it brings out, and this is a very unique feature of industrial engineering. It looks at a problem of managing the organization as an integrated systems of men, methods, and equipment. In many times, this holistic view or an integrated view, integrated systems view, is often missed out. And one of the major problems of low managerial effectiveness in organization is due to looking at a problem from a narrow subsystem perspective, only from the human resource perspective, or only from materials perspective, or only from equipment machines perspective. It says that managing resources, be it men, materials, and equipment, are all integrated. Everything affects everything else, and therefore, industrial engineering philosophy integrates, looks at a problem in its totality. And this indeed is one of the USP of industrial engineering, if seen in practice. The same is the philosophy of operation research, which I'll be talking about. So, systems approach to management of the organization, which indeed is one of the major drawbacks in managing organizations in complex systems today, because everyone looks at a problem from their narrow subsystem perspective. And often, as a result, many managers belonging to the same organization but different functional areas look at the same problem from a different lens. And this leads to many times the conflict of objectives in the same organization. Industrial engineering approach looks at a problem in its totality. Then it says, the next sentence it says, it draws upon specialized knowledge and skill from physical, mathematical, and social sciences, together with principles and practices of engineering analysis and design. Now, what does it indicate? This definition, this part of the definition indicates that there is no uh, limitation on the use of any kind of knowledge in any domain of knowledge, so long as it helps in achieving industrial engineering objectives. And therefore, uh, uh, industrial engineering has a very vast toolkit in terms of the body of knowledge that it employs in attaining its objective of enhanced productivity, so that it borrows that specialized knowledge and skill, be it from physical sciences, from mathematical sciences, and social sciences, together with principles and practices of industrial engineering analysis and design. And therefore, if you look at the national education policy, which talks about multidisciplinarity of exposure of engineering students, so that they should not only simply be exposed to technological subjects too, they should have a multidimensional exposure to uh, other aspects, because industrial engineering inherently incorporates that concept of multidisciplinarity, because in addition to the principles and practices of engineering analysis and design, it borrows from physical sciences, borrows from mathematical sciences, borrows from social sciences to achieve its objectives of enhanced productivity. And therefore, this is a subject which has enormous flexibility in adopting from whichever body of knowledge which helps us to attain the goal of maximizing the productivity or eliminating wastages or whatever its objectives are. Then what does it? What purpose does the industrial engineering approach serve? It says to specify, predict, and evaluate the results to be obtained from such system. So what it says, it specifies, for example, the targets of performance. You want to set up the goals for what should be the goals or targets of performance to be accomplished. You specify the goals for the specification of the performance of an organization. What is an optimal degree of productivity that you can get from these resources? You can specify that this is what we ought to be receiving. And once you have a specification of goals, then you can evaluate to what extent have you been able to achieve it. Predict, it can forecast, it can it can predict and forecast what kind of performance are we going to get, and evaluate for performance appraisal. It can evaluate the results to be obtained from such systems, and therefore you can apply industrial engineering in setting goals, in making in estimating prediction or predictive forecasting the potential performance, and actually compare for the purpose of control, evaluate to what extent an organization is able to achieve its objectives. And now therefore, if you look at, and this is the oldest definition, in 1957, which Indian Industrial Engineering Institution, and if you look at the journal, Industrial Engineering Journal, published by IIIE monthly, at the inner back page, this definition is reproduced. Now, if you understand this correctly in the way I have explained, perhaps there is no major room for improvement in it, except that, and I've suggested this to the National Council of Industrial Engineering to incorporate in it. Of course, uh, in terms of the resources of men, metals, and equipment, you can add in other resources like information, for example, is considered as a resource now. Information is a resource. Space is a resource. And any other resource that is required. And in terms of the principles or body of knowledge, perhaps in addition to social sciences, you can actually add life sciences or biological sciences into it. Reason being that earlier we were considering that engineering sciences and life sciences have nothing in common, which indeed, in my opinion, was a very wrong way of thinking, because life sciences and engineering sciences are so tremendously have potential of interacting and learning from each other, so that as you know that by now many of the computational algorithms are based on inspired by biosciences. Bio-inspired algorithms or bio-inspired management practices, bio-inspired engineering, and therefore there's a lot of uh, you know lessons we can learn from life sciences or biosciences, and many methods and techniques of computational and system design and performance measurement can actually be obtained. And therefore I had suggested that to increase the converse of the body of knowledge, although it's fairly broad as you can see, but we could build increase it in including biosciences in addition to social sciences, so that the point here is that you could be practicing industrial engineering by borrowing from any body of knowledge, not necessarily confined to engineering, so long as it achieves the goal of maximizing the performance of an organization by way of maximizing productivity, uh, uh, delighting customers, reducing costs, eliminating waste, uh, uh, managing time, and all that goes with it, or resource optimization. Now, this indeed was the conventional industrial engineering, I call it industrial engineering 1.0, which primarily owes its philosophy from Frederick Winslow Taylor, who actually got the title of Father of Scientific Management. And many of the industrial engineering subjects taught around the time I was studying in IIT Kharagpur. From in 1966 to 68, I was doing my master's degree in industrial engineering and operational research. There, much of the focus was primarily working at the uh, operations level, at shop floor level, primarily concerned with increasing labor productivity to getting maximum out of the manpower that's engaged. And therefore, the concepts like work study, methods engineering, time and motion studies, wage incentives as an instrument of incentivizing people to enhance productivity. And therefore, many of the conventional methods of industrial engineering were taught at that point in time. And therefore, subjects like methods engineering, uh, uh, time and motion studies, work study, wage incentives, job evaluation, merit rating, all those concepts were very popularly plant layout, facilities layout, plant engineering. These were the topics generally taught at that level. That's a conventional industrial engineering, and perhaps it was its limitation, perhaps perceived limitation was that this was seen to be only working at the operations level or the shop floor level. That's why in some places industrial engineering is also known as operations management or production operations management. In the Eastern Europe, industrial engineering is more popularly known as production economics. So there are departments of production economics. There's an international journal, Production Economics, very famous. IJP, one of the top-notch journal, is still called International Journal of Production Economics, which primarily is an industrial engineering journal. And therefore, it's known by different names, but the focus of industrial engineering 1.0 was this conventional focus. While it was good at that point in time, the business environment was not very competitive. External environment of doing business was fairly, stable, and the focus was of industrial engineering of those times was primarily to enhance labor productivity, and particularly since it emanated from American context where labor is costly, this was picked up. But then sooner or later, people got a wrong notion, and to my mind, this is also contributed to the narrow perception people have about industrial engineering, because they think that these are people who are only cut out for reducing manpower. Reducing manpower is not an objective for industrial engineering. Generating gainful employment can, because if your business increases, it in turn would, what it aims at is eliminating wastage of every kind and every resource. It aims at eliminating waste of time, waste of money, waste materials, and waste of manpower, waste of information, waste of space. So any resource, it's a war at eliminating wastage of every resources of any kind. And if there is a wastage of resources of manpower, so be it. But then it does not mean that it eliminates jobs. Because of enhanced productivity, it improves the system performance and increases the potential growth of an organization, generating more employment. And therefore there was a huge amount of confusion created by this. They thought that these are people who are cut out only for cutting down jobs. That was not the intended. The true, and this way it's good to understand the true concept of industrial engineering. And that's why I begin with this definition, because if this is it, I see still now I can, in fact, I'll be very happy to debate on this. Not anything contained in this conventional definition is still outdated. Only thing is it need to be understood and appreciated in that perspective. It looks at a problem in its totality. You apply this concept across the entire chain of design, installation, and improvement of ongoing systems, and apply all kinds of resources, primarily use any body of knowledge to specify, predict, and evaluate the results. And therefore, primarily, it's productivity engineering. Productivity engineering, quality engineering, cost engineering, all concepts are inherently contained in it, because eliminating waste, enhancing productivity, enhancing cost, uh, uh, reducing cost, enhancing value, and eliminating waste. And that's why I said these concepts that industrial engineering aims at will never be outdated. But unfortunately, as the time went on, the industrial engineering definition, because it was only perceived to be in that spirit, wage incentive design, layout, plant layout, but that's a very conventional and limited to only shop floor. That to my mind was a major limitation, perceived self-imposed constraint. To me, industrial engineering approach is as much applicable at the strategic level of decision making as at the technical or at the operational level. And therefore, to me, the same philosophy can be applied right from strategic or policy formulation level to technical to the operational level. And therefore, there's nothing that limits its application only at the shop floor level. Although we must know that the true value addition in any organization really lies at the shop floor. It's only at the operating level, only the people who work on the job, they truly add value to a product or a service. Rest of the higher level of the institution, organizational hierarchy, enhances the in supporting that value addition process. But the true value addition truly takes place at the shop floor level, and therefore operations are not to be undermined. But many times we have lost out our competitive advantage by undermining the operations, and even in business schools, by undermining the operations management area over the preference to the other more uh, fashionable topics. To me, the real value addition does take place at the operations level, and operations is not only manufacturing. Operations level in any function. For example, there is an operation level in marketing, there is an operation level in finance, there is an operation level in manufacturing, there is an operation level in project. The true value addition is where the things are added, the actions are done, tasks are performed, and therefore, although it was intended to enhance the productivity of operations, but it does not limit its concept. And therefore, to me, first misconception people must take out is industrial engineering application is across the entire hierarchy, right from strategic, tactical to operations level. And therefore, this was a major first industrial engineering revolution. It became popular those times, but later on, uh, other fashionable areas of management took over this. Then came second phase. I call it industrial engineering 2.0. This was an era of industrial engineering and operations research era with a focus on optimization. And that's why I said IIT Kharagpur, where I studied in from 66 to 68, I'm tech in industry. My degree is in industrial engineering and operations research. Now, this integrating industrial engineering and operation research, actually, if you look at the definition of industrial operation research, indirectly it conveys the same philosophy, because except that in operations research, the focus is on mathematical modeling and optimization. Mathematical modeling and optimization with linear programming, all its variants, queuing theory, simulation, included both in manufacturing and service systems and its ambit. And therefore, as you know, that linear programming was first developed by Danzig in 1939, and became so extensively because if you look at the potential application of linear programming and its variants, now of course it's no longer confined to linear programming. There are huge amount of including in the VUCA world, intuitionistic fuzzy programming and all that goes with it. But you must understand that the linear programming or mathematical programming is one of the most uh, potential tool, because it says in general, whenever we wish to allocate our limited resources to various competing demands, how to do it optimally boils down to solving a mathematical programming model. And therefore, starting from linear programming and the application of queuing theory in World War II, uh, which remained confined to the defense services till 1955, but then it was found, and therefore from 1955 onwards, industrial applications of operations research became very popular. And that's why IIT Kharagpur, as one of the, I consider my alma mater, IIT Kharagpur, as the mother of all IITs, being the first IIT. They were the first one to introduce, in 1962, this master's program in industrial engineering and operation research, which still continues and is one of the very popular program. Now, therefore, this I call it as industrial engineering 2.0, because here the focus shifted from uh, routine operations level of qualitative work study type into mathematical modeling and optimization. And optimization and mathematical modeling became very popular tool. Operations research became very popular tool in optimization resources and linear programming, transportation model, assignment model, inventory control, queuing theory, computer simulation, decision theory, decision tree, all that goes with that game theory. These were all mathematically, mathematical models. Again, the intended objective was same. Optimization here was find out the best way of doing it. In fact, and if I relate the industrial engineering phase 1 and 2, even in Taylor's method of scientific management, Taylor talked about find out the one best way of doing the job. That one best way of doing the job is what you call optimal here, one best way, and therefore what you call optimum or optimal solution to in operations research was one best way of finding the job in the conventional industrial engineering, and therefore there was no once again conflict, and that's why industrial engineering and operation research. Now one may wonder as to why these two, this and that. The reason being, conventional industrial engineering did not uh, focus so much on optimization using mathematical models. In operations research, uh, again, in fact, operation research is an application. In fact, we look at the definition of operation research is an application of mathematical tools, techniques, uh, uh, for solving the problems of operation of a system with a view to provide those in control of the system with the optimal solution to the problems. And therefore, again, systems philosophy, looking at a problem in its totality, but focus on optimization, and therefore systems thinking, which is inherent in industrial engineering, was still valid in the concept of operation research. Operation research is the study of the system as a whole. When we do the mathematical modeling, but with the purpose of optimization. And therefore, the difference between industrial engineering 1.0 and 2.0 is a greater degree of focus on mathematical optimization. And therefore, these techniques, and once again, I remember when I started teaching operation research in IT Delhi in 1968, we had a part of master's program. We had three courses in operation research, one, two, three. The techniques are enormous. And therefore, once again, like industrial engineering, the techniques of operation research are again not limited to few. These are, in fact, it's still growing. And as the business environment becomes more and more, turbulent, more and more fuzzy programming and fuzzy techniques and intuitionistic programming techniques, and still now newer methods, and that's where bio-inspired optimization techniques are coming, like artificial neural network, genetic algorithm, particle swarm optimization. Uh, all these are bio-inspired optimization methods, and that's why I suggested that if we include the word biosciences in the conventional definition of industrial engineering, it would further enhance the catchment area of the potential applications of available body of knowledge in solving those problems. And therefore, this was second revolution of industrial engineering. Again, during those times, it became very popular. In fact, I remember in the courses that are delivering, I was delivering in 1968 onwards in in operation research. There was such a huge enthusiasm of people from various other branches of engineering and IT Delhi were opting for learning operations research as a subject, and many times uh, the people interested in learning OR was more than the capacity of the room. And unfortunately, once again, and I'm saying professionally, we have perhaps not presented this. So, in the process, what happened? A lot of people with uh, high degree of mathematical orientation uh, joined the bandwagon, and therefore, a society like you have Indian Institution of Industrial Engineering practice from headquarters in Mumbai. A new society called Operational Research Society of India came up, ORSI. It has its headquarters in Calcutta or Kolkata now, and once again it has its branches all over. And therefore, uh, to me, these two societies primarily intend to achieve the same goal of optimizing system performance, looking at a system as totality, and therefore perhaps that integration of industrial engineering operations such as the IT Kharagpur thought of would have been a more logical proposition. But then the ORSI, the Operational Research Society of India, uh, and I'm a member of both, because to me, uh, I would ideally would have looked at both of these integrated into one. But then to me, both are important because there's a role that mathematical modeling and optimization serves in improving the system performance. But then operations research in due course of time, I don't know whether you've seen the, like you have industrial engineering journal coming from IIE. There is a journal called OpSearch published by ORSI from Calcutta. And although this is one of the very highly respected uh, internationally valued journal, in which it actually now Springer has taken over the publication of the journal. But then, uh, uh, and, and fortunately, the trend is now recent times is improving, and there is more application. There's much more mathematical complexity, and therefore OR was perhaps uh, uh, brought incorporated a huge amount of complex mathematical modeling, so much so that even for simple routine operational problems, we were expected to formulate in highly most complex, and to my mind that has done the damage, because the degree of model complexity should be contingent upon the importance of the problem. For operations level problem, the shop floor level problem, we do not need a highly complex mathematical optimization models. We simply need heuristic, simple, enlightened rule of thumb, which can help us to achieve our near optimal solutions, because the strict optimality is not important. As you can see, the sensitivity analysis of optimization would reveal that the optimal solution is always robust and it's plus minus 10% deviations around optimality. It does not cause any violence to the system. And as a result, perhaps the model complexity should have been in proportion to the level at which so when you're applying OR at the strategic level of decision making, any amount of complex modeling is no issue, because I must be right first time, because strategic decisions are those which would impact the organization for all times to come. And once implemented cannot be easily done. The cost of opportunity cost of going wrong is very high, and therefore at solving strategic decision making problem, any amount of complex modeling is no big deal. But for routine repetitive operational problems of the ongoing transaction level, making a highly complex model actually is counterproductive and would perhaps scare people. And that's why perhaps making operational level problems far more complex perhaps did a negative role. For example, just give an idea. In 1971, a paper was published, and my very good friend, and he was 1 year senior to me in IT Kharagpur, one of the most eminent professional now settled in America. In fact, he's been a president of Decision Science Institute and president of Production and Operations Management. Very brilliant person. But part of his research was on job shop scheduling, of flow shop scheduling. Now, flow shop scheduling, as you know, is to there are a number of jobs available and they have to be scheduled on various machines. It's an operational problem. But if you make a very complex model of this flow shop scheduling, that model published in Obsess, the journal I'm talking about in 1971, which did attract even a reaction from the reviewer. All this is I'm permitting publications a beautiful mathematical piece, but this is hardly going to solve problems on shop floor, because if you solve a flow shop scheduling problem by structuring it as a non-linear mixed integer programming, the non-linear mixed integer programming, even non-linear programming is more difficult than linear programming. There is no general solution. Integer programming is more difficult than linear programming. Mixed integer is more difficult than integer programming, and therefore structuring a flow chart problem as a non-linear mixed integer programming actually is an overkill of the complex modeling for an operational issue. So therefore, because of that complexity, I'm also telling why in the same IIT Delhi now, uh, there are many times when you offer a course on operation research, you do not sometimes even get, unless it's compulsory course, you do not get sufficient number of people to opt for this course. Why this loss of interest? Because we also need to address, the whole purpose is to find out the best use of resources by optimization. So concept optimization is great, looks at problem's totality, finding out the best solution under the constraint. That's what optimization will make. But where did we go wrong? Because we perhaps made operating level issues far more complex in modeling than was needed. And instead of attracting people to apply these, it scared people. Practicing managers felt very uneasy and using very complex mathematical model, and therefore, although in the beginning it was picked up in a big way, like same enthusiasm as Taylor's work study, but because of overdoing the complexity at the operating level and ignoring the strategic issues, because strategic, I must say why we ignored the strategic issues, because most of the mathematical models of operation research primarily were linear programming and variants, but single criterion optimization. A single criterion optimization at best can be applicable at the shop floor level. When you look at a problem of the strategic level, for example, where to locate your factory, what is an optimal location of a plant, facility location problem is a multi-criterion decision making. You do not set up choose a location based on a single criterion, and therefore uh, uh, all the conventional methods of OR primarily was single criterion optimization, and implicitly were applicable at the shop floor level, and making them more complex is counterproductive. But the strategic level, where multi-criterion optimization becomes important, were ignored at that point in time. And it's only in 1980, with the advent of AHP, analytic hierarchy process, which is an extremely wonderful multi-criterion evaluation techniques, and therefore AHP and now ANP, analytical network process, and a number of other TOPSIS and there are dozens of multi-criterion techniques that have come up now. Fuzzy AHP, using the ambiguity of the business environment, and now it's only after 1980 that the multi-criterion techniques of operation research relevant at the operation at the strategic level became important. So because of that reason, even too much of complexity, even that did not. Then came third phase, Industry 3.0. Now here, these were around in the late 80s, where many of the uh, 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 manufacturing systems with a primary focus on value or customer orientation and quality or value for money. So with quality orientation, as the advent of competition, you can see as the competition increases, customer aspirations went up. And this way we look at in the early point in time when there was not much competition, the customer was primarily going by the cheapest. Then he wanted quality without paying more, value for money, and value engineering came to being. Then flexibility. He wants to tell you what kind of product he wants, and therefore then a quick response manufacturing. Then you know, uh, so a lot of techniques such as total quality management, uh, quick response manufacturing, which led to SMED, single minute exchange of dies, the Japanese system. For example, in order to provide flexibility, where even one product, one unit would be an economic order quantity, to knock out on setup time being non-productive time, because an industrial engineering approach is a real attack on all non-productive, non-value adding activities. Setup time of the machine being one of the most non-productive time, which is consuming expensive equipment resource by not producing anything. So the entire focus in bringing that flexibility to manufacturing, where you could produce whatever a customer want in whatever quantity, whenever quick, and the response time became a competitive weapon. Because of those in increasing aspirations of the customer, techniques of total quality management, setup time reduction to the extent that single minute exchange of dies, leading to just-in-time JIT, with zero inventory systems. Pokayoke system of technology, where Pokayoke is a Japanese term which says even by mistake you do not commit a mistake. Error proofing, so that even by human error you do not even if a person by mistake presses a wrong button, the system prevents him from being implemented, and therefore even and therefore okay, that even by mistake you do not commit a mistake, so you produce zero effect, single element exchange of dies, total quality management, Kanban system of the Toyota production system. Toyota manufacturing system became a very famous tool, which became Kanban system. Low inventory or zero inventory system, or just in time, flow line production system, cellular manufacturing system, lean supply chains, flexibility and response time, value for money. These were the issues that became very important. And this I call as Industry 4.0, 3.0, Industrial Engineering 3.0. Now, many of these concepts are still popular because to that extent, these do contain all the previous two eras of industrial engineering. And therefore, in total quality management, once again, the word total means holistic. So, be it conventional industrial engineering, being OR or being TQM, the focus on systems thinking or totality, total quality management, refers to creating a culture in the organization where you have create what of total continuous improvement. So therefore, TQM refers to total continuous improvement. The total means involving everyone, right from top floor to shop floor. Continuous means never ending. The journey to quality is never ending. It's like riding a bicycle. The moment you stop, you fall. And therefore, journey of quality is never ending. It's not a project. It's not. It's a never ending journey. And improvement is the basic philosophy. In fact, industrial engineering can be called improvement engineering if you wish. Therefore, improvement has three dimensions in TQM: elimination of waste, that anything, uh, and we developed a very beautiful definition of waste in the process of, there's a definition that we developed in one of the project that PhD thesis that I guided in IT Delhi long back in 1984. Because conventionally the term waste we only look at from the output end. rejections, rework, scrap, damaged goods, uh, scrap we call waste. Now, waste can be at the input level, and therefore the general systemic definition of waste we gave, that any unnecessary input or any undesirable output from a system is waste. And therefore, waste is, in a more generic term, any unnecessary input. So, consuming more money than you should, consuming more material than you should, consuming more people than you should, consuming more space than you should, is waste. And this is what industrial engineering definition from the conventional revision key. And therefore, industrial engineering is a war on waste of all kinds. And that's what TQM also suggests: elimination of waste of all kinds. Second is reducing variations. Reducing variations, standard deviation is a parameter of inconsistency. Therefore, giving a consistent product quality all through, you require to reduce variations, standard deviations, and thus came the concept of Six Sigma. Again, is a Six Sigma is a very powerful technique, basically intended to reduce the process variations or variability. Variability is a real culprit in quality, and therefore reducing various variations uh, and innovation. Third is innovation. Find out all out-of-box solutions to the problems by involving technology, and this led to a business process reengineering. So that think of drastically different way of achieving the same goal by using the technology, and therefore business process reengineering, innovation, so that you are able to achieve a quantum jump instead of incremental improvement, and therefore concept of total quality management, elimination of waste, single minute of exchange of dyes, poka system. These were became buzzword. Cellular manufacturing systems, where a situation which looks a job shop like can be converted into flow shop has a inherent advantage, and therefore lean supply chain management with zero inventory or no inventory system. These concepts or industrial engineering 3.0 is still relevant and is being talked about in a big way. And to that extent, perhaps it's a current paradigm in which we are working. But unfortunately, the challenges of industrial engineering, which I, in fact, I have, for example, there is a crisis of identity in industrial engineering. Now, many of the techniques of industrial engineering involve management concepts. And to me, industrial engineering and management are two sides of the same coin. Every engineer eventually becomes a managerial role. And management is integral to all the two, because management is planning, organizing, directing, control. And management being a planning, organizing, directing, control, inherently every engineer has to be a manager too. And therefore, in teaching institutions, uh, for example, my industrial engineering and mechanical engineering department, that's where I studied in IT Kharagpur. Later, it became a separate department now. In fact, they renamed it as Industrial Systems Engineering in recent times. And the director of NEET, Professor M.K. Tiwari, who is a professor of that Industrial Engineering Systems Engineering, IT Kharagpur. But if you're located in a conventional department like my department is in Mechanical Engineering, IT Delhi, perhaps either due to lack of proper appreciation of the subject, uh, conventional engineering department, if industrial is located there, do not really treat this as a very important subject. Many times people say, oh, it's just common sense. Of course, a very good response to such people I give is, common sense is really not that common as the name implies. In any case, common sense is extremely important resource of a person. One should never lose of it. And all industrial techniques and are primarily intend to reinforce your common sense or intuitive judgment. Finally, the intuition or intuitive judgment of a manager that works. And all these techniques are intended to help you sharpen your intuitive judgment, and therefore is not to undermine. And therefore, engineering departments do not give it that much importance. In the business schools, they don't even consider it's not a management subject. So neither it's given engineering nor management. There are many misconceptions about industrial engineering. Anyone working in industry is an industrial engineer, as I mentioned. It has not reached all sectors of the production. Many times it's a misconception that is only applicable to production. That's why there are some common, in fact, even a BTech program in IT Delhi goes by the name of production and industrial engineering. Now, in GATE also, you have a specialization for GATE as production and industrial engineering. While it's important to integrate production and industrial engineering at a BTech level, it does not limit its application to manufacturing. Is as much applicable in agriculture, rural development, small and medium enterprises, logistics, transportation, warehousing, public distribution system, cold chains, hospitals, just name it, any system. And that the application of industrial engineering to other systems has not fully penetrated. Although I understand that in some of the at one point in time, uh, Tata Group of hotels were involving industrial engineering in the industrial engineers to improve the system performance, and therefore the conventional application of industrial engineering remains confined to manufacturing or to some service, but it's various sectors. To me, as a generalization, anything worthwhile that you are doing, industrial engineering has a role to play. Now, therefore, imagine such a powerful technique or concept which is applicable across the functions, manufacturing, service, in every sector, and looks at every problem in its totality to eliminate waste, enhance productivity, improve quality, delight customers, manage time. Why should it not be given the kind of attention it deserves? And that's my line. And therefore, as a result, the kind of enthusiasm people had in industrial education is now dying. Uh, BTech, MTech, and faculty development program in industrial engineering are no longer the most sought after they used to be. And I have been even say that like IIMs have multiplied. There are 23 IIMs now. The NITI, which was set up as one of the most prestigious institution in industrial engineering in 1963 with the ILO, still is a standalone institution, NITI. And indirectly, if you look at that, if you succeed in a profession, it multiplies, it grows. Like IIMs have grown, but NITI hasn't grown beyond its single location at Mumbai. And therefore, as a result, these are the challenges to that. And in order to overcome these challenges, because to me, as I mentioned, that I am a passionate industrial engineer. I have I never feel it will ever be outdated. It's not a fashionable subject. It's the most wanted subject, and in my perception, industrial engineer should be the first one to be hired in an organization and last one to be fired, because when chips are down and you're not doing very well, it's the industrial engineering philosophy alone which will take you, because you'll knock out non-value adding activities, you'll knock out flash, you'll knock out wasteful products, wasteful time, wasteful resources, and that's the way of coming back. And therefore, with this philosophy, I come to you now to bring the concept of industrial engineering 4.0 by reimagining industrial engineering and technology management for value creation. So therefore, industrial engineering and technology management for value creation, we need to reimagine. And therefore, philosophy of industrial engineering will never change. It's focused on elimination of waste, reducing cost, improving quality, enhancing productivity, delivering value, and delighting customers by offering goods and services that are better, cheaper, safer, faster, and producing more from less for more. Now, these are very noble objectives of any organization, and perhaps the only way of remaining competitive in a highly fierce competitive business environment, and the only way of making our local products globally competitive. And therefore, it's time that we bring back the lost glory of industrial engineering back to energize our manufacturing and service sectors to become globally competitive. And to my mind, that's the way that we can truly make Atmanirbhar Bharat, by making Indian products and services globally competitive. Because if you can do all that philosophy of industrial engineering proposes, by offering goods and services that are better, cheaper, faster, safer, and producing more from less for more people, this indeed is a way, and therefore this focus would remain. However, the focus, methods, and techniques of IR, industrial engineering, are contingent upon external environment of business, the changing nature and aspirations of the customer due to global competition, exponential increase in knowledge doubling every 2 years, disruptive technologies, and changing nature of employees, changing nature of employment, changing nature of the organizations with hybrid virtual organizations, network structure, globally networked, organization, highly networked, interdependent, knowledge-driven world. Obviously, in order to remain relevant, industrial engineering also needs to reimagine itself. And with that reimagining, I in fact bring that fourth avatar of industrial engineering, which is called Industrial Engineering 4.0. And some of the specific changes that are taken in the business environment, for which in industrial engineering 4.0 has to develop itself for it. The business environment is increasingly becoming VUCA, volatile, uncertain, complex, and ambiguous. Customers are becoming highly demanding, bordering on almost seemingly being unreasonable. You see, earlier they were on the receiving end, because whatever you give, they no choice but to take it. If you say you want quality, you have to wait. But because of the increased competition which has empowered customers, now customers are becoming highly demanding, almost bordering on seemingly being unreasonable. To give an idea, for example, earlier he said, okay, I'll buy a product which is cheapest. Price was the only determinant. Then he says, I want quality but without paying more. He wants quality without paying more. So a high quality at a lower cost. So value for money became important, and that brought subject of value engineering into domain. Then in the 80s, he says, yes, I want quality without paying more, but I don't take it whatever you tell me. I'll tell you what I want. So he'll prescribe the what kind of product he's looking for, and therefore he wants flexibility of choice. It's not that either leave it or take it. He'll say, I want choice of the product. So you give me, these are 10 different products, I'll decide which one to choose. So he wants flexibility. So quality, cost, flexibility, all are important. Not either or, all are important. Then you want, earlier you say, if you want quality, you have to wait. So you are booked in buying a Vespa scooter or a Fiat car for years. You say, no, I want quality without paying more, and I'll tell you what kind of product I want, and I want it immediately tomorrow. I'm not willing to wait. So this led to the impatient customers. And why were they becoming seemingly so demanding? Because they had a global competition, had one answer. If you don't do it, somebody else will. And that somebody else can be in any part of the globe. And empowered with that high degree of global competition, customer aspirations became increasingly high. And then when you give them flexibility, I mean response time, quality, cost, all, then even then he said, no, now I want environmental friendliness. He says, no, I'll not buy a product from a particularly many European countries. uh, they're very very conscious of the kind of technology that you use in producing products. For example, they say, I want you to use clean technologies, green technologies, and not technologies which are environmentally friendly technologies, so that in addition to being quality, price, and response time, flexibility, now he says he's environmental conscious. He says, I'll not buy from you if you are using polluting technologies. And therefore there came the concept of clean green technologies, sustainable technologies. And in the turn of this millennium, after even green production, green technologies, green productivity, green supply chain, all these became, and these are the terms that are mostly commonly used being now: green technology, clean technologies, green, productivity, green supply chain. Now he's again said that, okay, you have to be socially conscious, so that you are not using child labor. In fact, a lot of carpets from Bhadoi, from Belgium, I read somewhere, no first-hand idea, was perhaps not accepted because somewhere they had an impression that you were using child labor to produce those carpets. So therefore, socially aware, and therefore, as a result, today's customer is highly demanding. And because of that, why this highly demanding? Because global competition empowers them to be on the driving seat. Therefore, to satisfy or delight such customers better than their competitors do, you need to be using the state of the art methods and techniques of producing better, safer, cheaper products which are value for money. And therefore, as a result, you need to reimagine the newer avatar of industrial engineering, which I call industrial engineering 4.0. The disruptive technologies, which are now currently virtual reality, artificial intelligence, 3D printing or additive manufacturing, collaborative robots, Internet of Things, industrial Internet of Things, cloud computing, augmented reality, cyber physical systems, blockchain, and distributed ledger technology. Now, these are some of the technologies of what is known as Industry 4.0. The prime reason for me to prepare this lecture. So today's world is talking about these disruptive technologies because they have given way. Conventional methods of industrial technologies is now actually becoming cyber physical systems. I'll deliberate on that, and therefore it's a new opportunity for industrial engineers to gear themselves and reimagining the industrial engineering and redesign industrial engineering philosophy to incorporate uh, themselves, their role, space. Because as I mentioned, even in these disruptive technologies of virtual reality and cyber physical systems, we still need to be having productivity, cost reduction, eliminating waste. So those fundamental objectives for industrial engineering have not become irrelevant. Therefore, in order to make industrial engineering relevant, you need to be relevant in these disruptive technological era. And this is what industrial engineering 4.0 philosophy I am propagating. Then changing nature of work from home, short-term contract, project-based outcome orientation, multicultural work, network organizations. All these are the kinds of, and based on that, I now therefore propose, and this is my proposition. One can add on to it, and one can disagree with it, or one can refine it. As I'm very open to that. Now, industrial engineering 4.0 approach, therefore, philosophy remains the same. Industrial engineering approach the same philosophy of productivity enhancement, customer delight, etc., systems approach, optimal resource management. All those concepts are there. So, industrial engineering approach. So, your approach in industrial engineering 4.0 is approach or philosophy remains the same with focus on customer delight and systems approach in optimal resource management for efficient and effective design of industrial environment with data-driven decision making in Industry 4.0 environment. Now, this is how I propose the concept of industrial engineering 4.0 so that in a globally competitive, dynamic external environment with data-driven decision making. So again, the concept of operations research empowered with data-driven data analytics, business analytics in an Industry 4.0 environment. Therefore, in the again, it focuses efficient and effective. Efficient deals with optimization resources. Effectiveness deals with goal accomplishment, and therefore, uh, this is how I look at the industrial engineering 4.0. The key focus of this industrial engineering 4.0, that's why I call it the new paradigm. It is industrial engineering in an integrated cyber physical technological systems of Industry 4.0, but retaining fundamental concerns of productivity, quality, cost reduction, waste elimination, and customer experience in a globally competitive world of business. So, philosophy remains same as industrial engineering 1.0. No change in the philosophy because there cannot be any change in that philosophy ever because it's going to be almost eternal. So long as you have business, this concept has to be. But in a changing cyber physical technological systems of Industry 4.0. Now, this is a very quick overview. As you know, that Industry 4.0, 18th century, the Industrial Revolution, first Industrial Revolution, Industry 4.0, beginning of the 20th century, third Industrial Revolution through the use of electronics and IT, further progression in autonomous production, and now fourth Industrial Revolution. In fact, one of the most recent one in 2011, in Industry 4.0 concept was brought in Germany, and therefore yeah, the three earlier phases of industrial revolutions, industry 1.0, 2.0, 3.0 are 1760 to 1840 ushered in mechanical production, railways and steam engine. 1870 to 1940 mass production, electricity and assembly line. 1960 to 2010 computers, semiconductors, mainframe computing, personal devices and internet. And now industry 4.0 is in fact I'll be talking about. And therefore the industry 4.0 in the context in which I'm applying industrial engineering is a collective term in technologies and concept of value chain organization based on technological concept of cyber physical systems, the internet of things and internet of services. It facilitates the vision of smart factory with modular structured smart factories of industry 4.0. Cyber physical systems monitor physical processes, create a virtual copy of the physical world. We call it, digital twin, and make decentralized decisions. The concept of digital twin is a very powerful way where you simulate the physical world in a digital world so that you can experiment on the digital twin without disturbing the reality. Is a very effective way of evaluating alternative options till you see the optimal one. Over the Internet of Things, cyber physical systems communicate and cooperate with each other. So in the Internet of Things, everything, every component, every machine is able to connect and cooperate and communicate with each other and humans in real time. Via the Internet of Services, both internal and cross organization services are offered, and therefore these are intelligence, smaller and powerful sensors and machine learning. Now, these are the cyber physical systems in which industrial engineering is proposed to be applicable. Combines is a system of collaborating computational elements controlling physical entities. So, collaborating computational elements controlling physical entities is a cyber physical system, is physical and computational informational. A CPS deals with physical and engineered systems whose operations are monitored, coordinated, controlled, and integrated by computing and communication core. They allow us to add capabilities to physical systems by merging computing and communication with physical processes. So you can see uh, in cyber physical systems, computation, communication, and control. That means eventually computational capabilities communicate to control physical entities using information. This indeed, and as a result, the kind of major six design principles of Industry 4.0, which will be is interoperability, the ability of cyber physical systems uh, uh, to connect with each other, humans and smart factories to connect and communicate with each other via Internet of Things and Internet of Services. Virtualization, a virtual copy of the smart factory, which is created by linking sensors data. Decentralization, the ability of cyber physical systems within smart factories to make decisions on their own. Real-time capability, service orientation, and modularity. Modularity, as you know, is a very powerful, flexible design. These are the essence of it, and these are the building blocks. That means when you're talking of Industry 4.0 and using this to Industrial Engineering 4.0, these are the emerging building blocks of Industry 4.0: autonomous robots, simulation, horizontal and vertical system integration, industrial Internet of Things, cyber security, additive manufacturing or 3D printing, augmented reality, and big data analytics. There are some of the, and of course, blockchain and uh, uh, cloud computing are the other things that collaborating robots. Now, therefore, all these are impacting all aspects of value chain. And since industrial engineering is primarily concerned with enhancing the productivity of value chain from a vendor to customer, all these dimensions would be impacting the entire value chain, which indeed is given in this diagram. But then my focus would be on maybe on its potential applications would be robot assist production, predictive maintenance, additive manufacturing of complex parts, machines as a service, big data driven quality control, production line simulation, and smart supply network. Now, assets optimization would play an important role. Industrial engineering has always been concerned with the improving resource optimization. Therefore, in the Industry 4.0, assets optimization. So the kind of skill sets that the people, and that's what, in fact, you can see in the first in 2020. That means in current times, the kind of skill sets our employers would be looking from our graduates from engineering and management schools would be which are the priorities have changed to some extent. You can see, for example, the kind of 10 top skill sets which are relevant to be industry ready in the current Industry 4.0 environment. Complex problem solving. The moment you look at a problem in its totality, the problem tends to become complex because everything affects everything else, and therefore your capacity to find out a solution, a fairly good enough solution to complex problem. So a skill of complex problem solving, critical thinking, creativity, out of box thinking, people management, coordinating with others, emotional intelligence, judgment and decision making, service orientation, negotiation, and cognitive flexibility. Flexibility of approach, flexibility of choice, flexibility to learn, pick up an alternative, out of box thinking. Therefore, top 10 skills that will be required and industrial engineers to become relevant in current emerging paradigm should be able to focus in acquiring these skills to become industry relevant. And therefore, we need to reimagine design of work systems, cellular manufacturing, additive manufacturing, lean systems, collaborative competition. That means now, in fact, it's happening already. To deal with a global competition, you need to collaborate with your competitors. Indeed, and this indeed even in the National Education Policy NEP 2020 brings out collaboration amongst institutions within the country globally. So anybody with whom you thought was your competitor, we join hands with him or her, the company, as an institution, even academic institution can do collaborative competition. If you know somebody, some other college who used to be your competitor is able to offer certain outstanding quality courses because of the new flexibility that the national education policy gives you, let these courses be taken by your students from that college, and your strength in which you are the best resource institution, your courses could be taken by them. So in a way it's a win-win proposition that the best offers best services, and therefore its time has come when you collaborate with your competitor. So collaborative global supply chain instead of competitive supply chain. So win-win proposition, short working hours, cooperative teamwork, automation of routine functions. You think big. Let the routine operational issues be automated. The machines and computers should take care, and the people are able to spend time in thinking big, and so that strategic decisions, tactical decisions, coordinated decisions, performance measurement, progress chasing, inspiring people should be the time that managers should spend instead of spending time on routine. So routine functions could be automated. Robots doing only hazardous jobs. Now, in Indian context, we should handle robots very carefully, because the moment you use robots for replacing people, there'll be a negative reaction from, because anybody who loses job does not care so much for the modernization of your equipment and machines. So therefore role space for robots and people. So robots should be doing hazardous jobs where putting man power is not ethically correct. So when the job is risky, for example, if you are doing underwater welding or you're doing a very hazardous job, or you're working in a potentially radioactive environment, let robots do hazardous jobs, uh, save people doing it, and people do jobs which are non-hazardous. And so there's a role space for robots as well as people. More strategic outsourcing, jobs which is your core competency, you do it yourself. Jobs which are not your core competency, you outsource. Again, it's a win-win, it's a collaborative competition, so that everything doesn't need to be done every time. For example, earlier, for example, in our even IIT's system, as you know, IITs are almost townships. You're managing almost municipal operations like water supply, shopping, housing, maintenance. Everything is being done. Hospitals, residences, hostels. Your core competencies can be done by the institution, and the other service functions can be done outsourced by people around. And therefore, this way you create a network of institutions working in a hybrid by outsourcing your non-core activities. Of course, strategic outsourcing also, it doesn't have to be blending, so that you're able to devote more time on your core functions. Now, in many engineering institutions, a lot of faculty time is spent in doing non academic work, by doing routine things, by outsourcing that non-academic work to professionals as service providers. The faculty could use its intelligent time in being creative, in finding out newer methods, conducting path-breaking research, and using their creative time and routine administrative functions at times make them lethargic in performing research. And therefore, this way, by more strategic outsourcing, we're able to devote far more, so that everybody does what is who's good in it. Academics should do what they're good at, the researchers should do what they're good at, and any other non-core function can be outsourced, and therefore more focus on strategic outsourcing. Pull-driven system, demand-driven decision making, pull-driven supply chain, customers, competitors driving decision making. Because as you know, delighting your customers better than your competitors do, you need to know what your competitors are doing and what your customers want, and therefore your decision making process will be driven by customers at one end and the competitors by the other end. They are the purpose for which you are there, and therefore big data, operation research, algorithmics, more intuitionistic, multi-criterion simulation, artificial intelligence, uh, genetic algorithms, artificial neural networks, hierarchy process, analytic network process. These are some of the emerging techniques under operation research which are more relevant now compared to classical single criterion deterministic optimization such as linear programming. And that's why, since I mentioned, in order to remain relevant in business, it's time that institutions start teaching to their students more relevant decision making techniques which are more relevant in current times under current technological scenario, rather than teaching outdated limited techniques of conventional techniques of those times. And this way remaining current uh, is will be far more useful than traditional deterministic optimization techniques such as linear programming. Then you have to rethink your products and services, reimagine customer experience, and reimagining value chain. And therefore, in the process, for example, maybe what you need to do not re-engineer, reimagine. So you are going beyond re-engineering. Reengineering is set up new technological platform for customer engagement and back office. Of reimagining is enabling to conceive business freshly. Look at the business in its very different way, in line with capabilities that are digital technologies give them, connecting to the customers that was never possible before. With the help of digital technologies, we're able to connect with customers that are never possible before. For example, I'm able to speak to you without ever meeting any one of you, without ever visiting your premises. I'm able to connect to a fairly large number of people logged in, hopefully from all over the institutions. And therefore, it's the empowerment of the digital technology which indeed empowers me to reach to a much wider cross sections of the audience compared to what was conventionally possible in a classroom setup. So therefore, you have to reimagine providing services and facilities to conceive business in a very fresh, different way. For example, and there's a reason, even in academic institution, and I must mention that industrial engineering techniques are as much applicable in management of academic institutions as anywhere else, because academic institutions are also service systems. And I must tell you that whichever positions I've held, I was as a vice chancellor of UP Technical University, Lucknow. I applied many of these industrial techniques in the management of the UPTU, and it made a different transformational impact on the way you are doing your management of your systems. And therefore, there's so much potential applications of industrial engineering techniques even in the management of the academic institutions, because academic institutions are also service systems, and therefore we should be able to reimagine, uh, instead of simply re-engineering, to look at our way of delivering products and services uh, freshly in line with the capabilities that digital technologies give them, connecting to the customers that was never possible before. For example, now with the online video mode, of course, uh, our limitation in this setup, the technological setup that we have between you and us, and at times I do feel sad about it. Although better technologies are available. For example, I would have been very happy if I could see all of you. You could see me, and yet I could continue presentation. Right now, I'm presenting my PPT. I'm not able to see any one of you. Maybe some are listening, maybe some are not listening, maybe some are logged and listening, some are logged and not listening. But then, to make best out of it, perhaps if we evolve technologies where we almost simulate a classroom condition, where I'm able to look at all people I'm speaking to, and they could look at me and we could talk to each other in real time. And if that happens, look at the tremendous technological reach that reimagining of work can give you, and able to reach even the unreached institutions in the low in the rural areas, or even in different countries. And I can, in fact, a person from outside the country, the best of the professors from anywhere in the world could come in and speak to you. These are the enormous possibilities of connecting to the customers that was never possible before. Therefore, reimagining business means creating many conditions of startup, the sense of freedom, flexibility, and creativity, but the scale and discipline of a large enterprise. You may be a small, operating. That's why in the current times, the acreage of an institution, of an academic institution, no longer relevant. For example, it's no longer relevant that you have 100 acres of land. What is relevant is connectivity. For example, to me, acreage has given way to the connectivity and the bandwidth. From smaller space, you could be playing a global role across the world, and therefore that's the kind of the out of box thinking is required, and therefore the even a startup sense of freedom, flexibility, and creativity, a scale and discipline of a large enterprise, and therefore small companies in a small space perhaps could be visible across. Bring cross-functional teams that can ideate, bring to life, and execute a truly digital user experience. Do everything to enhance user experience. Ultimately, finally, the user experience. And if I was able to connect to you I could see your face, I could see your eyes. Uh, Perhaps I could know whether you are able to relate to what I'm saying. Otherwise, I would have changed my wavelength, because I speak to the audience depending upon the wavelength that they are at, and therefore we should do everything to enhance user experience. It also means continuously measuring and testing the impact of these products and services, and learning from results, not learning from results. Empathies with end users, expand the brand and value of proposition, and design for next 3 years, but build for today. Now, therefore, what is important in the VUCA environment? You cannot plan for a long period. You can't know what life would be 5 years from now. But you design for next 3 years, but you build for today. New structures and teams, and use digital technologies to energize your culture. Therefore, you need to reimagining value chain, reimagining assets utilization, optimization, and reimagining operations. And this is what the industrial engineering, disruptive technologies of biotech, nanotech, neurotalk, green, renewables, ICT, mobile technologies, 3D, AI, IoT. These are now buzzwords in current times. Sensoring and speech technology, drones, big data, cloud, virtual reality, augmented reality, blockchain technology. All these will be disruptive technologies, and industrial engineering 4.0 primarily makes use of that. And this is where the implications of that on IE 4.0. Therefore, the kind of the focused work area where industrial engineering must develop itself into that area. I now give you some of the areas which we need to work. For example, we need to design personalized, flexible artisan customization. Now, one of the major advantage of digitalization has been what is known as mass customization. Even in educational institution, every student is an individual, and how to customize, personalize, flexible customization, design things so that everybody gets what one is looking for. Develop new business models, B2B linkages, develop local supply chains, and they are globally competitive. New production spaces, connected factories, new markets, new sectors of coverage. You reach the area which you not reached earlier. Find new markets. Sustainability issues like people, profit, and planet. That the sustainable, the 17 SDGs Sustainable Development Goals. People, profit, and planet. Now these are three. Now, as I mentioned, a company or even an institution, an academic institution, must not look at profit. You look at holistically. Once again, industrialism philosophy of looking at things totality or objective is people, profit, and planet. It's called triple bottom line. So conventionally, you only think of profit, but then that's not it's a great culture of an organization. Look at people. What are the people? Your employees. your students, your employers, your society, and therefore profit, but not at the cost of people. So that, and indeed now it's working out very clearly. Only delighted people would give you delighted performance, customer satisfaction. If your employee is unhappy, he or she will not care for customer satisfaction. And if you really want customer delight, make your people delighted, make your employees delighted. If you want your students and if you want your students to be delighted, make your faculty delighted, make your employees delighted, which in turn would delight your students, which in turn would delight the employers. And therefore it is people. And third is planet, environment. In the rat race of making profit, do not exploit resources which actually erode the environment, the physical environment or climate. So people, profit, and planet is called triple bottom line, is now emerging as an important sustainability issue in every organization. And this makes industrial engineering multi-criterion. As you know that industrial engineering deals with multi-criterion. The goals are not single profit, is people, profit, and planet. Then design of smart factory systems, mass customization for customer delight, enriched customer experience. Now, customer delight actually, the chain of earlier we used to call customer satisfaction. Now we call customer delight, and now we further call customer experience. Is the experience, if a customer gets, is a delighted customer, is what is your objective. And the methods of big data analytics, fuzzy intuitionistic algorithms, and optimization, machine learning, all this will be important. Distributed ledger technology, blockchain. Right now, blockchain is a concept which is coming up in a big way in a financial transactions, but it does involve the concept of cryptocurrencies. For the moment, right now in India, cryptocurrencies is not a legal tender, although in some countries like Japan, Australia have allowed it. Therefore, challenges before industrial engineering profession is to reimagining design, operation, and maintenance. Same thing which I started with the original definition. The challenge is therefore in the current business environment of Industry 4.0, Industrial Engineering 4.0 is to reimagine your work systems. You redesign your products. So reimagining design, operation, maintenance of cyber physical systems for efficiency and effectiveness, for great customer experience. And therefore, industrial engineering in traditional systems of Taylor's era considered industrial systems as isolated, self-centered, and approaches were reactive. Whereas in the current age, these are not isolated, these are connected systems. These are not competitive, they are collaborative systems. And therefore, in the current age, these are connected, collaborative ecosystems and are responsive. Future systems will be ubiquitous, intelligent, and proactive. In that kind of systems, and since industrial engineering and operation research are systems approach to problem solving, future systems will be ubiquitous, intelligent, and proactive. And therefore, the implications of this, for example, in supply chain domain, earlier solution was focused on improvements at the enterprise level. Now we see trends towards integration and more responsive supply chains that can participate in a wider connected ecosystem. In the future, the intelligent supply chain would be proactive. You'll be have with the help of artificial intelligence, we'll be able to make our supply chain intelligent, which will be proactive in self-correcting, in self-healing when disruptive events occur. So I can imagine a future intelligent supply chain with the integration of artificial intelligence will be proactive instead of reactive, and self-healing in case something goes wrong, will be have the capacity to repair itself. Disruptive events occur with cryptocurrency flow through decentralized ledger technologies. Now the kind of work scenario itself would change, because industrial engineering deals with work system design. The work itself might change, and therefore in order to know what kind of work system design industrial engineering should deal with, you should know the concept of what kind of future work is going to come. Current transformational world of work today, the digitalization, globalization, demographic change, education, migration, and transformation of people's values and preferences. The values and preferences of people are changing. Organizations increasingly becoming multicultural, and therefore managing diversity would become an important component. These forces will drive change, because digitalization, globalization, demographic change, education, migration, and transforming people. In fact, as must have mentioned earlier, that demographic dividend of India perhaps is such a powerful potential that in many parts of the world, Indians who are globally employable would actually be manning those organizations, and therefore migration of people who should then learn to manage diversity and varying cultures. These forces will derive the change of work design. Key challenges and therefore tensions characterizing the world of work would be work with opportunities and risks associated, such as will digitalization enable work for all? Now, these are genuine concerns. If I go in for digitalization, will I be able to give work for all? Here, I must mention that any technology must not knock out uh, the work from people, because if that happens, people will become disruptive. And therefore, while we have disruptive technologies, but constructive people who will use these disruptive technologies in out of box thinking of finding out the relevance, so the nature of work may change. This will call for skill upgradation more frequently. The nature of work would change, but all these digitalization must not eliminate work, but they must enable work for all. Data protection of employees, this is becoming a major data security, data privacy. As the digitalization work, industry 4.0, industry 4.0 in a digitalized environment, and the country is seeing a huge amount of digitalization focus, but the concerns that need to be addressed, and these challenges have to be addressed by industrial engineers as well. How to ensure data protection of employees? If humans and machines work together, how can machines empower people? Therefore, in fact, the current scenario may be now in Industry 4.0 paradigm, machines can talk to each other, robots can talk to each other, robots can collaborate, machines can collaborate, but people must also talk to each other. If only machines talk to each other and people do not talk to each other, it's a disconnect. And therefore, as a result, these are the issues that how can man and machine together can interact, empower, and therefore machines, how can they empower people? Flexibility in working in terms of times and place. Now, for example, organizations have to also change their mindset towards working conditions. Working at different points in time, at different places, gives that desired flexibility of working hours. And perhaps this rigid mindset in the current uh, Indian organizations, including academic institutions, a focus on rigidity of time, because time rigidity of time was relevant at some point in time. What is important is that people must deliver value, and therefore certain degree of flexibility in working hours, in working conditions, in working times, even in working place. Work from home, for example, work from home is increasingly becoming important, and even people, even faculty in an institution must be encouraged to work from home. Even AICT has to change its criterion of approving institutions, with a conventional focus on architecture, architect driven, square meters of room size, the stair size, the ramp size, and all that goes with it, and the ratio of the student to faculty ratio, because with the digitalization and online, and a single professor can talk to connect to thousands of students, and therefore these conventional mindsets of even approving institutions in the light of emerging technological paradigm, we have to also change our mindset and bring flexibility in terms of working hours, in terms of working place. It's not necessary for people to come to the conventional single place. In fact, you may be working in a highly networked virtual organization where people are at different locations. They might have never met each other, and yet they're working as a very powerful tool, united by the digitalization. And therefore, this flexibility in working in terms of times and place, future factory, ensuring participation and security. Issues like work-life balance is becoming important. Now, people, employees, particularly in the Western world, And now even in India, I'm told very in recent in some of the conclave that I attended that people working from home are so used to working from home for last 2 years that they are really finding it difficult to go to the office and workplace. They are all used to that life because now perhaps and therefore issues like workplace work life balance, finding fulfillment in the work also need to be reimagined. You have to create work which is not routine and boring. And therefore, industrial engineers would have, as a part of work design, industrial, as you know, deal with job design, work design, and designing the work systems, designing the work system, work design, create a work, the modules of work which people find fulfilling. And therefore, all this needs to be done, and our work design systems would be. Now, as a result, when I said that industrial engineering is losing its shine, this I perceive as a great opportunity for industrial engineering profession under industrial engineering 4.0 to leapfrog. Now, leapfrog, as you know, is a term used to make up for the past slow pace of development. And therefore, definition of industrial engineering has remained unchanged for past 60 years or so. The American Institute of Industrial Engineering, and the triple I definitions, and we have not revisited it ever since, despite changes in technology, process, and people. And therefore, this definition was such a fundamental definition that for the last 60 years we have not changed it. Although technologies have been changing, processes have been changing, people's aspirations have been changing, customers' demand have been changing in a globally competitive environment. Now, traditional industrial engineering was relevant at individual operations level. It did not talk about, I'm talking industrial engineering 1.0, Taylor's time. It did not talk about optimization, did not talk about efficiency and effectiveness together. Only talked of productivity, which is efficiency, but didn't talk of effectiveness. It did not talk of customers' delightful experience in the face of global competition in a somewhat hazy business environment. Thus, traditional industrial engineering became less relevant to the society in current times. And unless we revisit ourselves, we reconfigure industrial engineering to be in current with times, and unless our teaching of industrial engineering becomes relevant with the current times and ground realities, we would not be able to make this profession very. As I mentioned, that in my way of thinking, this will never be outdated. Our methods of dealing with it may be outdated, our techniques may be outdated, our approach towards practicing industrial engineering may be outdated, but the concept and philosophy of industrial engineering will never be outdated. And thus, if we follow conventional traditional industry 4.1 1.0 in a traditional Taylor's way of work study, time and motion studies, that is become less relevant now. And therefore, a lot of much, thus it got relegated into background or much hyped world of MBA trained managers from IIMs with focus on finance, HR, marketing, and advertising. Operations management remained a weak, even there. What in fact I'm dealing with? Industrial engineering deals with operations. Real value addition takes place at operations level. Because unless I produce a product which is marketable, which offers value for money, no amount of marketing can sell a non-marketable product for long. And therefore, those functions are required. I'm not undermining them, but they cannot overtake the fundamental value addition proposition at the shop floor level, because the real customer experience, particularly in the service sector where customer and service provider come in direct contact, is a real delightful customer experience that no amount of higher level functions can make up. And therefore, what is important, that operations management at the shop floor level, where industrial engineering is traditionally relevant, is a place where real value addition takes place, and therefore we must not undermine this in the name of a more perhaps glamorous functional areas of management, which indeed, and therefore they're required. I'm not undermining them, but then unless you produce a product which offers value for money, I bet any amount of advertising and marketing will not be able to do it. But if you offer value for money, even with much less marketing and advertising effort, people would come to you, because particularly Indians are very value driven people. They know they'll go to anyone which offers value for money. And generally, my own perception is, normally if you offer value for money, you don't need to advertise too much, because advertising has a role to play in only sensitizing that you are there in the market. But any amount of over advertising of a low value product is not going to turn your markets for long. And therefore, we need to have a focused attention to various functional areas. So, operations management is not to be undermined. As a result, reimagined industrial engineering 4.0, in my opinion, would leapfrog. That means the lost past glory, this subject, and I've been passionately practicing it. In fact, in uh, you might have seen from my profile, I was a joint professor in the Department of Management Studies in IIT Delhi, but I remained my main professor in industrial engineering and mechanical engineering department. I remained deep rooted in my technology setup, and therefore, your technological background that you have would give you a major advantage to leapfrog you as an industrial engineering, provided you are in touch with the ground realities of the emerging paradigm of technological systems, and the basic philosophy of industrial learning is an integral part of your value, of your thinking. And therefore, because of these advantages, industrial engineering 4.0 philosophy has an advantage over conventional uh, management subjects. For example, Industry 4.0 is technology enabled cyber physical systems with technological domain knowledge of industrial engineering will be an advantage over purely mathematical model driven world of operation research specialist. In fact, as compared to a purely mathematically model driven world of mathematician, your knowledge, technological domain knowledge of a subject as an industrial engineer would be an added advantage, and therefore you would have an edge on purely mathematical model driven over specialist. Integrated systems viewpoint. When you look at a problem in its totality, I would ensure you that you would have an edge over specialized functional areas of MBA managers who specialize in finance, marketing, HR, etc., etc. Because today, while those functions are important, but what is important to look at all these functions in a cross-functional way, and therefore again we are getting back to looking at a more generalized way, looking at a problem in its totality, and systems approach to management, where all these functional areas are integrated into system as a whole. It's which is a built-in philosophy of an industrial engineering approach, and therefore integrated systems viewpoint would have a edge over specialized functional MBA managers working in subsystems driven mindset in silos of advertising, finance, marketing, and HR. Because while these silos are important, but they need to connect and coordinate with each other, which many times doesn't happen because of subsystem thinking mindset. Industrial engineering philosophy being holistic and systems approach would therefore trained industrial engineers with integrated systems viewpoint would be able to look at the functioning of the organization in its totality, which is the need of the hour. Industry 4.0 is an opportunity, therefore, to place itself with the USP, unique selling proposition of integrated systems approach, design thinking, multidisciplinary knowledge base from mathematical, physical, social, and the biological sciences that I mentioned, and technology enabled cyber systems. It has to make itself customer centric and include operations to strategic level of management in all areas of human endeavor in manufacturing and service sectors in the era of industrial internet of things. So that's the wide converse. So all those wide converse of any area of human endeavor, manufacturing or service using in the cyber technology enabled cyber systems, the basic philosophy remains, and this is a place for itself. And to make it happen, industrial engineering education itself should be inclusive in terms of industrial system sciences, industrial systems engineering, and industrial systems management. So that when you teach industrial engineering, you should teach industrial system. System becomes a common denominator. Industrial system science, the science of industrial engineering, mathematical modeling, the industrial system engineering, and the industrial engineering systems management. So that science, engineering, and management of industrial systems, the objective for delightful customer experience through value creation and delivery. Creation is not enough; it has to be delivered to the customer. And this, therefore, is my concept of industrial engineering 4.0. which I thought I'll perhaps share with you. And uh, I don't know whether have I okay. Are you able to connect with me, or are you already logged out? Hello, hello.
Sir, we are connected,
You're
sir.
connected. So what do I need to get back to you? I have to stop sending this. Let me see. No, no, I'm not able to connect it. What's happening is okay. Yeah, okay. Now. Therefore, this is from me now, and perhaps that's the time for me to now, uh, address any issues and uh, concern and discussion that you may like to have. So that
Yes, Professor. Yes, yes. I'll put open to the faculty members and students for question sessions, Professor. Yes.
now I must mention, Dr. Natarajan,
Yes, Professor.
I'm addressing the topics that you're given to me,
Yes, sir. Yes,
and I
yes.
presume that the audience is able to connect with those topics.
Yes, Professor. All mechanical engineering students, aeronautical, automobile engineering students,
Do you have industrial engineering in your college?
courses we have, sir.
Not
Not
college,
not not
not as
branch.
a not as a branch. Okay,
Not a branch,
your
but we
courses.
have industrial engineering
Okay,
courses.
okay,
Yes,
fair
Professor.
enough. And to me, in fact, as you know, in IIT Delhi and Kharagpur, any
Yes.
branch of engineering can pursue masters in industrial engineering.
Yes, Professor. Yes.
And when I was studying industrial in IT, mechanical engineering, every engineering student had an exposure to a course on industrial engineering.
Okay, Professor.
There's
Okay.
a weight, in fact, because there has to be some concept of industrial engineering in every engineer.
Yes, Professor. Correct.
Okay.
Yes, questions, HOD?
Good afternoon, sir.
Malika Surendra. Okay.
Yes, sir.
Yeah.
Sir, I need a clarification.
Yeah. Yeah.
How the
Would it not
industrial
be a good idea, at least people who are asking question can show their video, so that I know at least I'm connecting to somebody who I can see, because that's something which, unless it's a problem with you, but they put never mind. You can if
Yes, Professor. Mallika Surendra, you can switch on your video also.
yeah, because it looks always good to connect to people to people. The connectivity is a keyword. Anyway, yeah, please go ahead, Surendra. Yeah, yeah. What happened? I'm not able to. Yeah, is connectivity issue with you? You can switch off your video if your connectivity comes in the way, because many times you don't have bandwidth to have both video and audio. No issues. I can understand those constraints. No issues. But then, yeah,
my question
yeah. Please, can you be slightly louder? I'm not able to hear you fully. No, your voice is broken. Maybe you have run out of the bandwidth, the data. I'm not. Your voice is broken. I don't know whether others can hear you. Hmm. No.
HOD, is there any problem in audio?
Yeah, I'm
Good
not able
afternoon,
to
sir.
hear him. Yeah, yeah. Okay.
Good afternoon, sir.
Good afternoon. Yeah, yeah. Loknath
Hello.
Reddy. Yeah, yeah.
Sir.
Loknath
Good
Reddy.
afternoon, sir.
Good afternoon.
Thank you for your valuable lecture, sir.
Okay.
Sir, my interest is to know that do we have the resources and staff to implement and manage this technology in all sectors of industry?
Now, actually, as you know, that this is now, in fact, the concept of industrial engineering, industry 4.0 itself is very recent. It's in fact in Germany, it's it's in 2011. This concept has come. And therefore, at this point in time, Industry 4.0 concept has not been fully integrated into an Indian scenario because it requires huge money. In fact, I had uh, the Minister of Heavy Industries had uh, uh, given me a consulting assignment to develop a roadmap for implementing Industry 4.0 in Indian context, because our Niti Aayog has been extensively propagating, and there have been large number of conferences on Industry 4.0. Now, therefore, since it's a huge amount of technological upgradation required, a huge amount of capital intensive nature, at this point in time, we are not in a position to implement Industry 4.0 in its totality. In fact, what I had suggested in my roadmap, that it has to be seen in a very phased manner, and first initially pick up the low hanging fruits, which does not require much of the uh, investment. And therefore, some of the things like, for example, artificial intelligence, cloud computing, 3D printing, are very, very easy and are not very capital intensive. And therefore, we should make use of it. And later on, you invest in technologies such like like collaborative robots or robot assisted manufacturing, etc., etc. So over a phase period of time, I believe by 2040, that means about 20 years from now, Indian industries would be fully geared towards adopting the, but then some of the low hanging fruits such as low cost automation, using artificial intelligence in a big way, because artificial intelligence is a major game changer, and it indeed is very, we Indians are very strong in artificial intelligence, and basically is it's using certain decision support system to bring some element of intelligence to the machines. And for artificial intelligence, low cost automation, 3D printing, or additive manufacturing are some of the, and cloud computing are some of the very important, and simulation, digitalization, virtual twins, artificial reality are some of the areas which indeed right now, and even AICT, if you look at, I don't know whether your college has been given, now AICT is bringing certain component of these knowledge right in the first year or second year of engineering education across AICT assisted institute. So these things which AICT and many of the the conventional department of computer science are now specializing courses on AI, AR, VR. They are doing it. So perhaps that kind of digitalization would help. But when it comes to uh, uh, collaborative robots or involving robots, to me that can get a lower priority, because we need to give work to people, and therefore not immediately but over a period of time. But when you look at a discipline, for example, why I'm saying this, why this industrial engineering 4.0 I'm talking about, that industrial engineers themselves have to revisit. So the techniques that you teach in your classroom have to be very different from what you were teaching maybe 30, 40 years back. And my own understanding is that perhaps there's a dearth of really qualified teachers in teaching industrial engineering. Perhaps anybody who has not been trained in industrial engineering is asked to teach industrial engineering would not be able to bring in the kind of concept which motivates people. And it's with that spirit that I'm primarily intending this lecture, for people to train faculty for teaching industrial engineering, who in turn would be able to inspire confidence in the students, so that this subject is truly relevant. It was relevant. I said that people used to queue up for admissions. And this, in fact, to my mind, even engineering institutions must look at it. Does not require that much of capital intensive investment in starting a course on industrial engineering, at least the master's level. And perhaps we need to do that. So right now in the short run, perhaps not whole of it that I've talked about, but I'm talking about a philosophy of future, how future industrial engineering 4.0 must adapt to this, since the industry 4.0 itself is emerging. It's on a nascent stage. Most people don't even know what does it mean, and therefore I'm trying to how industrial engineers should gear up for the future work. But already trends exist from work from home, digitalization, distributed network organizations. Some of these trends are already there, and therefore we must be able to use this industrial engineering philosophy in the current scenario. It's just nascent stage, not fully. Okay, it's a concept developed in the Western world. Perhaps they may need more robotics because their manpower is shrinking, their population rate is low. We in India need to focus more on eliminating waste, industrial engineering philosophy, reducing rejections, and therefore not eliminating manpower, not cutting down jobs should not be the objective. Otherwise, it'll fail. Cutting down jobs should never be an objective. Increasing quality of work, quality of job satisfaction, and increasing employment opportunities should be our objective, and it's doable. Okay.
That's it, sir.
Yeah.
Thank you, sir.
Okay.
Good afternoon, sir.
Yeah.
I'm Abdul Salam from Mechanical.
Yeah. 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 Please.
May I know the differ from industrial engineering and engineering management?
Uh, Engineering management and industrial engineering. In fact, my whole focus was on industrial engineering. If you remember, I gave a complete definition of industrial engineering. And engineering management, in fact, uh, is like technology management, managing technology, managing engineering. Does not look at industrial engineering holistic, the entire systems of men, metals, and equipment with a much wider canvas. Engineering management is only a very specific applications of industrial engineering in managing that technological system, that particular technology. So engineering management or technology management, in fact, they call it technology management, is a very small subsection, whereas industrial engineering is a very wide canvas, almost in engineering management only how to manage that technology. Industrial engineering tells you how to manage people, process, technology, and coordinate amongst them towards customer delight. uh, Engineering management doesn't talk of customer, doesn't talk of people, doesn't talk of process. Therefore, integration of men, methods, and equipment in a coordinated, because ultimately in any management is the people, process, and technology that needs to be done. In engineering management, you only talk of managing technology. Industrial engineering deals with managing people, process, and technology together for customer delight, and therefore much wider canvas compared to engineering management. Okay, all right.
Respected Professor, greetings
Yeah.
from Hindustan Institute of Technology. I am Gogil and this is my query. What will be the contribution of production and industrial engineering student in the implementation of Industry 4.0?
No, as I said that you first, in fact, the industrial engineering students would obviously make use of industry 4.0 context. Industry 4.0 deals with those new disruptive technologies, how to implement them, so that implement them by outsourcing at the lowest cost, installing them at the lowest cost, and making use operational to make it cost effective. So apply industrial engineering even in the adoption of those technology, because the definition of industrial engineering is all inclusive in procurement, choosing, picking up right kind of technology which would fit in your requirement. So right from selection of the right technology, right kind of focus, right priorities, everything would be relevant in implementing industrial engineering approach. In therefore the extent, for example, that's what I did when I developed a roadmap for implementing for industry 4.0. We applied which are the things which can be easily done without much of investment in the short run. That's what I call low cost, low hanging fruit. That's an industrial engineering. Prioritize your implementation. Developing right priorities is also kind of industrial engineering an approach. Because many times we do things with a mixed of priorities, and therefore industrial engineering, as I mentioned earlier, is as much applicable in anything that you do, including evolving the implementation of Industry 4.0 in with the right priority structure. For example, when I mentioned right now, don't invest much in capital intensive robots. Only when robots are required for hazardous work environment, do that. Let people be doing what they need to do instead of replacing them with robots. But empower these people with the help of those technologies to achieve much more. With limited resources, they achieve n times more, and therefore make them more productive. So use these technologies to make people more productive, but don't replace them unless the place where they are deployed are hazardous in nature. So they're going in for robots straight away. And in fact, I came across where, in fact, we are now even simulating. We have a robotic teacher. Now, I, for one, believe that a teacher cannot be robotized, because even now a robot cannot have the emotions and the value system and a character of a teacher. Therefore, replacing a teacher with a robot perhaps may not be a great idea. A teacher is a teacher. No amount of technology should therefore replace human beings. The technology must enable people to be more productive, enable them to achieve more, enable them to be more competitive, but not replace them. So therefore, I would perhaps give, you know, replacing people with robots in Indian context, in Indian economic scenario, is not a great idea. But then there are many great ideas. So pick up these 9 subsystems of in the right priority, and initially pick up those which are enhancing your performance, but do not cost you much. And that's what I named some of them. Okay.
Thank you, sir.
Okay.
Good afternoon,
Good
sir.
morning, sir.
Yeah. Okay. Is it who is Selva Muthukumar?
Yes, sir. I am
Okay.
Salom Kumar, sir.
Yeah. Selva
Uh,
Muthukumar.
will you please tell the difference between Industry 4.0 and lean manufacturing, sir?
Now, lean manufacturing. See, lean manufacturing. I did. If you, I don't know whether lean manufacturing was, is a conventional industrial engineering 3.0. It's being practiced in lean manufacturing. We actually look at uh, uh, knocking out the inventories in the supply chain. With lean is just in time, where I'm able to, for example, when you look at in lean manufacturing or lean supply chain, managing material flow through and into and out of the system with minimum inventories in the system. And therefore, lean manufacturing is also known as just-in-time manufacturing, or JIT, or low inventory system or no inventory system, because inventories are necessary evil in an organization. They erode, and that's why inventory management is an important technique of industrial engineering, where you in all forms of inventory as a necessary evil. It speaks of the money blocked in non-productive way, and industrial engineering is an attack on all non-value adding activities, and inventory being one such. Therefore, in lean manufacturing, we knock out inventories and almost produce just in time, so that whatever you need, whenever you need, wherever you need, you produce just in time. So lean and JIT are just the same, where the whole focus is on reducing inventories. Inventories being non-productive form of capital investment, where you're keeping material in the form of store, or in in-process storage, or in finished goods store, which is non-productive money blocked in a non-productive asset. And therefore, in lean manufacturing or lean in a production, our entire focus is to streamline the production flow in such a manner that we do not have unnecessary inventory at either of the stages of the manufacturing system, right into, through, and out of the system. And that's where in fact, when I talked about single minute exchange of dies, or JIT, because when conventional manufacturing was batch manufacturing, since you take 3 hours to set up a machine to change over the job, therefore you must produce at least a certain economic batch quantity. You produce at least 1,000 pieces, becomes an economic batch quantity. Less than that is not worthwhile. With lean manufacturing, You knock out the non-value adding activities such as setup time. That's why I talked about single minute exchange of dice, SMED, which Japanese are practicing in a big way, which was instrumental in making lean production system in Japan, or just-in-time total production system. So we have single minute exchange of dice. That means within a minute you can change over uh, one product from another product on the machine. So the non-productive time is only 1 minute instead of few hours. So even one unit becomes economic, one unit becomes optimal, and this is what you call it lean, because you only produce whatever you need, whenever you need, where you need, just in time, without holding any inventory. Therefore, inventory is an extremely important subject in the entire manufacturing systems, because you'll find that the inventory turnover ratio uh, is one of the most important competitive edge. All those companies which are doing very well have very high inventory turnover ratio, which means they keep very low inventory, which are lean. So only lean companies are more competitive, more competitive, and have greater value for money. If you keep huge amount of inventories in the system, you are not competitive, and therefore lean is synonymous to competitive manufacturing, because you are not keeping huge amount of inventories as a non-productive capital block in a non-productive form. And hence, but this indeed is not new to, in fact, that's industrial engineering 3.0. If you remember, in my lean is a part of that, which indeed lean, GIT, uh, green, lean production system is still very, is a part of conventional industrial engineering 3.0. But in industrial engineering 4.0, lean would still continue to be important. See, lean is from knocking out the fat, and fat is considered to be non-productive. Therefore, as a result, uh, the companies which are competitive will continue to be lean, even in industry 4.0, perhaps more lean than in an industry 3.0 environment, because in inventory and information are can be traded off. By providing right information on right time, you can reduce your inventories, and inventories can be replaced with information. Since under industry 4.0, information would be the major cementing force, which hopefully would make production system more leaner than the conventional information system flow. Therefore, even under industry 4.0 environment, lean would continue to be important topic, because to me lean means productivity, and productivity is the real end focus of any industrial approach in whichever avatar. And hence lean would continue to be important. But in conventional lean means reducing inventories, which indeed trying to cut down non-productive form of the money blocked in either at the raw material storage, or in process inventory, or finished goods inventory in the entire supply chain. Okay.
Hi,
Thanks,
sir.
Dr. Mansur.
Very good afternoon.
Good afternoon. Yeah.
May I know when a business should invest in Industry 4.0?
When should business invest in industry 4.0?
Yes, sir.
Yeah. If for example, if you're able to have the needed resources to invest, as it's a major capital intensive investment. If you don't have that, obviously you cannot invest in it. Therefore, as a result, do you have the money? And if you have the money, where should you invest that money? You need to prioritize, and that's why I said first invest in where, by investing in that, you get the highest return. So therefore, invest in uh, information systems, in internet connectivity, in low cost production, low cost automation, in integration of your information flow, and invest in in quality enhancement, eliminate waste. So on those areas you should. But if you have money in fully investing in the industry 4.0 as it is, to my mind, other than major manufacturing systems, such as, for example, in the OEM, the original equipment manufacturers in the automobile sector, for example, perhaps they could go in for many of the technologies of Industry 4.0, even though not fully, all of them, in fact. But then some of them can go in for robots assisted manufacturing, robot assisted assembly, and therefore major players in manufacturing, generally which are multinational companies or collaborations, which have the money, perhaps would go in for more percentage. But I'm not aware with any company in India can say they are fully geared towards Industry 4.0 at this point. The concept itself is new. Imagine 2011, only 10 years old concept in Germany. And therefore, a concept which in Western world is only 10 years old, to expect that concept to be immediately applicable in India, but it's futuristic, at least as learners, as people who are aware, and training people. For example, as I said, the global employability means that you train people may not be employable for the moment in India, but they the skill set which will highly be required in the developed world. In the developed world, there is a greater degree of technology penetration compared to us, because they are short of people and we are short of money for investing in capital intensive technologies. And therefore, while we can develop our students and futuristic technologies such as this, for which some of their employment prospects in the developed world would be sought after. But if you are looking for employment opportunities in Indian context, particularly for SMEs, only some aspect of this Industry 4.0, particularly low cost automation, uh, in computer assisted inspection for quality, for digitalization of your records keeping, coordinating process, people and technology, are some of the, but they are less capital intensive. So it depends upon which case. Right now, no Indian companies, in my opinion, are in a position to employ Industry 4.0 in toto. But it has to be a measured approach. Okay.
Professor, thank you.
Thank you.
I think there is no more questions.
Good. Great. Thank you.
Uh, uh, we will wind up the session, Professor.
Good. Thank you very much.
Thank you,
All the
Professor.
best. Thank
Thank
you
you.
very much.
Thank
Thank you
you.
very much.